Okay, good morning, class. I won't be in class tomorrow, obviously, or today, Friday. So I wanted to record a little lecture that you could watch over the weekend and over fall break. That way we'll be well prepared for next Friday for our exam. So today we're going to talk about mostly the Felkin-Anh. So that's Felkin-Anh and polar Felkin-Anh models for diaster selectivity. So models specifically diastereoselective additions to aldehydes and ketones. That's primarily what we'll be doing today. And so this will apply whenever we have a chiral aldehyde or ketone. So, for example, at the end of last class, we ended with this ketone here, in which we have an alpha stereocenter. And Professor Stevenson, when he introduced this example, he showed that basically, if we take this ketone and we reduce it to the alcohol with some hydride reagent, if we use lithium aluminum hydride, we have a 3-to-1 preference for the anti-diastereomer, and if we use L-selectride, we have an even greater 99 to less than 1 selectivity for the anti-diastereomer. And this was a little puzzling to us at first, maybe, because we know that lithium aluminum hydride is a quite small equivalent of hydride. It's not very sterically encumbering, whereas L-selectride, as we showed earlier in the last class, is a quite bulky and sterically encumbering borohydride. And we saw how this difference in sterics for cyclohexanones led to different selectivities in axial versus equatorial attack of this hydride equivalent. And so when we changed this acyclic system, we were a little perplexed as to why they give the same selectivity then. And so today we're going to learn the Felkin-Anh model, which will hopefully explain that. So let's start that. So in the Felkin-Anh model, we're going to consider just at first a generic ketone or aldehyde. So L So this is our generic ketone, or if R here is a hydrogen, we have an aldehyde. And L denotes the largest carbon group, or the largest R group, S the smallest, M the medium. And typically we can use A values to determine our L, our S, our M. Now, in some cases this will be trivial. For example, if you have a hydrogen at this stereocenter, then you know that'll be RS automatically. We can't get smaller than a hydrogen. If you have a T-butyl group or an isopropyl, a phenyl, a cyclohexyl, that'll, most of the time probably be your largest carbon group. So there's a lot of intuitive just grasp of the sterics of these groups from your prior knowledge of Chem 210 and Chem 215. Now, anyways, if we take this ketone or aldehyde and then we react it with a nucleophile, what the Felkin-Anh model says is that if we consider first, let's draw a Newman projection. I'll erase that right now. before we actually talk about Felkin-Anh, sorry, let's draw a Newman projection of this aldehyde or ketone. So as given in the starting material, we have Rl eclipsing our carbonyl, our S will be down here, our M will be down here. Okay. And so we know if we have a nucleophile now, that it will react at our carbonyl. So if we were to do a mechanism and we had a nucleophile, you would most certainly do this step first, in which the nucleophile will do a carbonyl addition, adding into the pi star we've learned from earlier classes of this carbonyl. Now there's going to be a transition state that is going to be favored by the Felkin-Anh model. And what that is in the transition state of this carbonyl addition, according to the Felkin-Anh model, we will have this preferred conformer. We're going to put our largest carbon substituent at one of the two perpendicular positions to the carbonyl. In this case, it'll be this position, and I'll show you why in a second. So we're going to rotate RL perpendicular, then RS and RM will rotate likewise. This will be our transition state. M and our S. Now, the reason we want this configuration where this conformer where RL is perpendicular in this manner instead of this manner is that our smallest carbon substituent, or in some cases a hydrogen, is going to be right over, if we consider the pi star of this carbonyl, when we have our nucleophile come in, it's going to have to approach at this angle where the pi star is, and this angle has a special name, which I'll get to in 1 second. And when this nucleophile approaches our pi star of our carbonyl here, the steric interaction with RS is going to be smaller than if RM were there. So, for example, I'll just quickly draw the other conformation in which the largest carbon group is perpendicular. So this is the sort of other possibility to putting RL perpendicular. But now if the nucleophile were to attack at this angle, it would encounter a steric clash with RM. And that steric clash is going to disfavor this conformation being the sort of transition state of our carbonyl addition. And that's why we want to put RS at this position so we can minimize this steric clash. And so what the Felkin-Anh model says then is whenever you consider your carbonyl additions, the largest carbon substituent will always be perpendicular to the carbonyl, and you will have the smallest carbon substituent or hydrogen in the trajectory of the nucleophile, so as to minimize that steric clash otherwise. Now, this angle at which the nucleophile approaches has a special name. So if we draw this here and we consider basically the angle here, here, and here. So basically the angle at which the nucleophile approaches that's going to be the theta, that angle, will be 107 degrees. This is a very specific number, and chemists, we denote this as the Bürgi-Dunitz angle. And just as a historical point, the way that the Bürgi-Dunitz angle was discovered is if we go back to 1973, Bürgi and Dunitz were looking at crystal structures of certain natural products like this. Here's just one example. So this molecule is called cryptopine. And what they found is when they were looking at the sort of molecules of this type, so they had, for example, different substituents at these positions. They had, this is basically a crystal structure that they obtained of this had a partial bond formed between the nitrogen at this position and the carbonyl here. There was a very sort of bonding interaction, so to speak, between this nitrogen and this carbonyl, and this basically resulted in the nitrogen being above the plane at about 107 degree angle of the carbonyl to the carbonyl. And since this was apparent from multiple different structures of this sort, there were about 6 examples in the paper. I'll leave it here. It's Journal of the American Chemical Society, 1973. And the sort of 6 structures they looked like of this sort, they always got their crystal structures having an angle between the carbonyl and this nitrogen nucleophile at 107 degrees, which led them to conclude that for carbonyl additions, the sort of ideal angle of approach for a nucleophile is at 107 degrees, which is why we then call it the Bürgi-Dunitz angle. So now we can get back to our example. When we finish this addition, one thing you'll also notice is that the approach of the nucleophile in this manner, in this specific conformer, leads to a completely staggered product going through the transition state. Which is to say that there's no torsional strain interactions in this transition state. Maybe you recall from the cyclohexanone addition examples, there were certain attacks, the equatorial attack, for example, in those cases led to a torsional strain as the O passed through the equatorial hydrogens in those cyclohexanone systems. In this case, our O is not passing through anything, our O is not passing through any group. There's no torsional strain in this transition state either. And that means that we lead directly to a staggered conformation in our product, Rn, Rl. And if we then translate this Newman projection back out into a sort of line structure, we will get this product. Okay, so our nucleophile will be anti to RL, putting it there. The R group that we had is now going to be anti to RM, which puts it on a wedge because RM is on a dash. And our OH here is anti to RS, or it's syn to RM, therefore it is on a dash. And so this is the Felkin predicted product, the Felkin product. So now what I want to do is that we've seen the model for the Felkin-Anh diastereoselective addition to chiral aldehydes and ketones. I just want to give us a few examples of this. Particularly, we'll be looking at, give me a second to erase. I guess while I'm erasing, remember the key thing is in this Felkin-Anh model, when you set up the Newman projection of your transition state here, you always want to place RL perpendicular, and you want to have RS being in the trajectory of where the nucleophile is going to come at your Bürgi-Dunitz angle. And that transition state structure is going to always give you the Felkin-Anh predicted product, which for most of the examples we'll be looking at will be a good model to explain the observed diastereoselectivity. We'll talk about the polar Felkin-Anh the polar Felkin-Anh model in a few minutes. So let's apply the Felkin-Anh model to a variety of examples. So if I give you this chiral aldehyde, with this nucleophile here, so this lithium enolate, we're going to predict basically what is the stereochemistry, not the stereochemistry, the configuration at this stereocenter. So we're not doing any chemistry at where this methyl group is. That configuration is not going to change. But when we add in this enolate, we are going to have a new stereocenter, and we want to determine its configuration. So let's first draw our Newman projection of this compound as it's given. Now, if we consider our phenyl group is going to be eclipsed with the carbonyl, and our methyl group should be there, our hydrogen will be there. Now, when we're solving these problems, we always want to rotate RL perpendicular to our carbonyl, and have our smallest carbon substituent, RS, or in this case it'll be a hydrogen, at Bürgi-Dunitz angle, which is going to be where our nucleophile will approach from. So let's just draw two possible conformers. We'll decide which one satisfies both these conditions. So the easiest condition to satisfy will be we'll just put our phenyl group perpendicular in both of these. In one case like this, the other case like that. So we have our two conformers where RL, the phenyl group, you can get that from our A value, is perpendicular to the carbonyl. And we have these two conformers now. But we can see in this second conformer, our second condition is not satisfied. So RS is going to be the hydrogen, smallest will be, the largest will be the phenyl, RM is this methyl. In this case, if we have a nucleophile, as we do here, our enolate, approaching from the Berge-Dunitz angle to attack our carbonyl, it's going to have some steric clash with the methyl group when it's in the trajectory. When the methyl group is in that Berge-Dunitz angle, you'll have an unfavorable steric clash with the nucleophile. And so this is not actually our reactive conformer. This is not going to be the model that we want to use based off the fact that our methyl group is not our smallest substituent, our hydrogen is. And so this is our reactive conformer for this chiral aldehyde. Here's RS, here's the Berge-Dunitz angle. That's about 107 degrees. I don't have a protractor, but close enough. So now when we add in our nucleophile, it's going to attack from that Berge-Dunitz angle. Hydrogen is a small group. It's our smallest group, so it'll have the least encumbering steric interaction with the hydrogen. Remember, this carbon goes from sp2 to sp3, so we're going to parameterize. If the nucleophile comes in at the Berge-Dunitz angle from this way, that's going to sort of push the carbonyl and hydrogen opposite to that way when it parameterizes. So there's our OH, there's our H, there's our nucleophile. Make that a little shorter. Since we don't do any chemistry on the carbon in the back, that doesn't change. Another key feature is that we don't have any torsional strain in this transition state because our O, when it passes this way, when it parameterizes, there's no group on the back carbon that interacts with. The hydrogen passes through, or when it parameterizes, there's no R group that it's going to have torsional strain with. That's a consequence of the Felkin-Anh model, as we talked about. We'll arrive at this structure as our product. I've all protonated our O. We did a acidic workup, H3O plus workup. And now we want to translate this back out into a line structure. What's nice is that our nucleophile, in this case, is going to look like this. Maybe I'll explicitly draw it here. So that's what our nucleophile is going to look like, because remember, this enolate will reform its carbonyl, and then the pi system will act as the nucleophile at the aldehyde. Excuse me. This gives us this product. So remember, we didn't do any chemistry at the back carbon, so that's going to stay the same. The configuration of that carbon will stay the same. If this carbon was on a dash, our OH is on the same face of this ring as that methyl group, which will put the OH also on a dash bond, or you could think the hydrogen that's at that carbon is anti to the methyl group. That's on a wedge. Either way, you arrive at a structure in which you have syn, a syn relationship between the methyl and the hydroxyl group. And actually I have a literature value for this. It's actually going to be 3 to 1, so 3, then we'll have our minor will be the anti-product So our minor product from this literature example is going to be the anti, and we can rationalize the observed ratio based on our Felkin-Anh model. I think what's critical is being able to translate your final Newman projection back into the line projection, the line structure here. If you have trouble with that, doing it directly from here, what you can do is rotate your back carbon back to its original position based off the given conformation, and then you can line your longest carbon chain anti to that, because that'll give you the correct line structure. Remember, we always want the longest carbon chain in plane. So you can return your back carbon to its original position. You can rotate the front such that the longest carbon chain on that front carbon is anti to the sort of longest substituent in the back. And then you can, it might be easier then to bring it back into a line structure from that Newman projection. If you're good enough to do it directly from here, then more power to you, and feel free to do that on the exams or the quizzes. Okay. Let's do one more example before we move on to the polar Felkin-Anh model. So here's another example. So we'll do, how about, so we'll take this chiral ketone, and let's react it with lithium aluminum hydride. So remember, this acts as an equivalent of H minus. And we want to predict then, once again, what will be the configuration of this carbon in which we add our hydrogen to, or that we add our hydride to. So once again, we'll go through that whole algorithm, so to speak, of the Felkin-Anh model. We're going to draw a Newman projection as our ketone is given. And then our methyl group will be there. So if we took a look at the A values of the methyl group, the isopropyl group, and the hydrogen, we would obviously conclude that the isopropyl group will be Rl, the methyl group will be Rm, and our smallest group will be hydrogen. Now we're going to rotate to, I'm going to abbreviate as the Felkin-Anh transition state, FATS, FATS. Remember, this transition state is the one in which our largest carbon group is perpendicular to the carbonyl, and our smallest carbon group, or smallest residue, is at the Berge-Dunitz angle. So we can consider, if we rotate Rl this way, then our hydrogen this way, and our methyl that way, we will in fact end up with our hydrogen at the Berge-Dunitz angle. and our largest group perpendicular. So this will be our preferred conformer for reaction. In this case, our nucleophile is H minus, or it's effectively H minus. It's going to approach at the Bürgi-Dunitz angle. Remember that name, Bürgi-Dunitz, or it's two names. Remember those names. We're going to parameterize this sp2 carbon, which means our oxygen goes that way, our ethyl will go that way. We immediately arrive at the staggered conformation, which means our transition state experiences no torsional strain, which is another reason why the Felkin-Anh model is good at predicting diastereoselectivity. selectivity. The idea is to minimize the energy of the transition state. Torsional strain is bad. It's an energetic penalty that will raise the energy of a transition state. So anyways, we're going to arrive then at this structure here. Okay, and I will, for the sake of giving an example of if you can't translate it straight back into the line structure, here's what you can do. You can do a sort of intermediate in which you're going to rotate your back carbon back to the positions at which it was given originally. That way you can be for sure that you're going to have the stereocenter that is already set correct. So we were given it like this, so I put it back like that, and now we put our longest carbon chain in the plane of our largest group, which is our isopropyl. In this case, our largest group will be the ethyl. So if I put my ethyl anti to that isopropyl group, my hydrogen is going to end up here. My OH will end up there. Yes, okay. And so now if we translate this back into our product, what does this look like? So, let's think. We have our methyl on a wedge. Here's our methyl. Our methyl is anti to the hydroxyl, which means our hydroxyl group must be on a dash. So that's how you can reason through it if you're not exactly good or you don't have a lot of practice already with being able to take these projections and sort of turn them on their side. But this is in fact what you would get if I asked you to project down this carbon. You know, all of you could certainly give me that this is that Newton projection. So either reasoning with wedges and dashes and the anti versus syn relationships, or just being able to take this and rotate it mentally in your head, or with a model kit. You're more than welcome to bring a model kit on the exam. You'll arrive at this as the Felkin-Anh predicted product. So there are some problems with the Felkin-Anh model, and this is where we're going to switch gears now into the polar Felkin-Anh model. Consider this reaction here. I give you this chiral ketone. This is called a TBDPS group. Oh, sorry, there should be 2 phenols. Tert-butyl diphenylsilane, or tert-butyl diphenylsilyl. It's a protecting group for alcohols. So I'll probably be abbreviating it as TBDPS. So this ketone. And then we react it with lithium aluminum hydride. Once again, that's an H- equivalent. If we look at the anti to syn, here's OTBDPS, H. So this will be our syn product versus the anti here. We're going to see that we get a 95 to 5 syn versus anti ratio. So maybe as a exercise, you could determine that the anti-product is actually arising through the Felkin-Anh model. And so we can see that this product is going against the Felkin-Anh predicted model. And so we have to now account for this difference in selectivity, in which we've gone from, so this is Felkin predicted, where we've gone from having our Felkin predicted product being the major diastereomer to now our Felkin predicted product is the minor diastereomer. So you might have noticed that in the case of this ketone, there's one really key difference between this and the ones that we've considered before. And that's the presence of a polar or electronegative alpha substituent. So things like oxygen, nitrogen, sulfur, chlorines, fluorines, things that are very polar and electronegative are going to give you the opposite selectivity from your Felkin product. And what we have to do then is, with our model, is account for why this is the case. And this is going to be the introduction to the polar Felkin-Anh model, which is a stereoelectronic model. So we'll revisit this example. We'll revisit it and complete it after we talk about the model itself. And by stereoelectronic, whenever you hear that word, Professor Stevenson said, you should automatically think, where are my molecular orbitals? Show me the molecular orbitals. Okay, so if we're given a ketone or an aldehyde, a chiral ketone or aldehyde, in which we have a, I'm going to just put X. X is going to be something like, typically O, N, S, halogens. Kind of said that weird halogens. We'll have R, let's do R1, R2, R3. Well, no, sorry. I take that back. We'll do Rm, Rs. The polar Felkin-Anh model is going to predict that the preferred transition state structure, when we do a Newman projection, set that up, will be the one in which the polar bond is perpendicular to the carbonyl. So you can think of the polar Felkin-Anh model as almost like the Felkin-Anh, except our polar bond, our CX bond, will be automatically taking the place of our largest carbon substituent. And we're going to see why that is in 1 second. So first I'll just project this real quick. So we will get Rm there, and then X here, Rs there. And so if this is the conformer as given, when we rotate, we're going to put X perpendicular, and we'll still have our smallest residue at the Berge-Dunitz angle where our nucleophile will approach. And that can only be satisfied from this specific conformer. Remember, there is another conformer in which our X is perpendicular. It'll be over here, but then Rm is at the Berge-Dunitz angle, which is a bad steric clash for when our nucleophile approaches the carbonyl. So you can think of this as X as, RL. Our CX is going to act as the largest carbon substituent. And this is a result directly of the molecular orbitals and their energies. So we know that the sigma star CX, I'm going to draw that on our structure here, a little bit smaller. I'll shade. Essentially, in this conformation, our low-lying sigma X, sigma CX star, low-lying sigma CX star can overlap with pi star. So I've drawn pi star, and there's the lobe of sigma CX star. In fact, we can draw a sort of perspectival rendering in which hopefully it's apparent that when this CX is perpendicular to our CO, our carbonyl, you can have perfect alignment of those orbitals, perfect overlap, and this is going to be a sort of stabilizing interaction. So this is going to lower the energy of our transition state, and whenever you lower the energy of the transition state, you're going to favor whatever diastereomer or whatever isomer is the product of that transition state. That's going to be a key concept in kinetics. The lowest energy barrier in your transition state is going to be what determines the stereoselectivity of your reaction. And so we know that, for example, that a CX, where X is O or N, because O or N is more electronegative than carbon, for example, those CX star orbitals are at a lower energy than the CC sigma stars, and therefore they're better able to interact with the pi star system of our carbonyl. So remember, polar bonds will have lower energy orbitals than a nonpolar bond. We learned that earlier in the class, and that is still coming up even now. So this is a stereoelectronic when we're considering how the molecular orbitals align and interact in space. And so if we took a nucleophile and then had it approach at the Bürgi-Dunitz angle, what we would get for our product then is this structure here, nucleophile, okay. Let's turn this back into, let's turn this into a line structure. Remember, we didn't do any chemistry at this carbon, so when we redraw it as our product, we don't have to change the configuration there. And now, if I look, my nucleophile is going to be anti to X, which will put it on a dash. And our OH will be syn to the polar X group there, putting it on a wedge. So this would be the polar Felkin predicted product. So I want to go back and do an example. I said I'd do the example that I used to introduce, but I'll actually leave that for you guys. I'll do another example instead. Sorry for being unclear in that manner, but I realize that I'm probably over 50 minutes by now. I just want to give a different example than the one I gave earlier. So let's consider this ketone, this aldehyde here. Two methyls on our nitrogen here. Okay, so let's do a Newman projection down our carbonyl. Our carbonyl is given to us upside down, which not too big of a deal. Sorry. This way. That's where we're looking down. Our R group then is like this, eclipsing our oxygen. And I'll probably end up denoting this as R as we go through. This is going to be R for the rest of the problem. Our nitrogen group, N-methyl-2, is going to be there, and our hydrogen will be up there. Now we're going to apply the polar Felkin model because we have a CN bond. So a CN bond is a polarized bond. We know nitrogen is more electronegative than carbon. Therefore, you're going to have a lower lying sigma star orbital that, if it's perpendicular to the carbonyl as we've drawn it here, you'll have a very favorable energy interaction in which the sigma star is overlapping with the pi star of our carbonyl. And so let's draw that conformation, that Newton projection. That's going to occur when the nitrogen is perpendicular in this manner, because that'll put So if we put our nitrogen perpendicular in this manner, over here, over there, our hydrogen, oh, whoops, I flipped the carbonyl. Please disregard the past, 45 seconds of this lecture. I flipped our carbonyl. That would have been disastrous. So, never mind these arrows. We want to put the nitrogen perpendicular in this manner, such that our hydrogen then is going to end up at our Bürgi-Dunitz angle for the attack of our nucleophile, which I didn't even give. So let me. Oh boy, I'm sorry guys. I should take a step back and give you the nucleophile. That's our nucleophile. And then we'll have what I've called R, which is this group here. Now, in the Felkin-Anh model, you might have predicted that this big R group, this sec-butyl group maybe, I think, would be in the perpendicular position because it's going to be sterically larger than a N-methyl-2, a dimethyl nitrogen group. And we could predict that because we know the atomic radius of nitrogen, because it's more electronegative than carbon, because it has more protons in its nucleus, is going to be smaller than carbon. So we would predict that actually this nitrogen group would be sterically a lot smaller than this R group. And so by the Felkin-Anh model, we would never put it perpendicular. But because of the stereoelectronic effects we talked about in the polar Felkin-Anh model, we put our polar bond perpendicular, and we still have our smallest residue at the Bürgi-Dunitz angle for attack. And so we'll arrive at this structure, or this projection here, when we pyramidalize. Got office hours in 30 minutes, better hurry up here. We get this structure, our nucleophile. Remember, this is the enolate of an ester. So it actually is going to look like this. The methyl ester. Okay. So let's translate this back into our line structure. I'm going to do it in which I rotate everything back to as it was given, and then put the longest carbon chain in plane. So rotate. So when we were given, our long R group was directly down. Our hydrogen and our nitrogen groups were in that position there. Now, our R group is going to be the longest. In this case, we'll want to put where our nucleophile came in as anti to that, because this is the longest substituent in the front carbon. And if we do that, then we will arrive at this structure. 1 second while I rotate in my head. H here, and the H here. Let me make sure of that. So that there, that there, that there. Yes. Good. So we'll arrive at this projection, which is going to be so remember, we didn't do any carbon. We'll keep that stereocenter the same. We didn't do any chemistry at that carbon. We'll keep that stereocenter the same. Likewise for where our polar group was. Okay. And then we are going to have a carbon where our OH is. And so if we want to determine where's our OH, well, it's anti to our polar bond group. So that'll put it on the wedge. Just make sure. Yes, so I didn't mess that up. I did it before in my notes, as any good professor, well, I'm not a professor, but as any semi-adequate teacher as I am will do. I did it in my notes beforehand, and yes, we get this structure, which is predicted by the polar Felkin-Anh model. So I've given you now a couple examples of the Felkin-Anh, an example of the polar Felkin-Anh. The important takeaways are, in the Felkin-Anh, you want to put your largest carbon residue perpendicular to the carbonyl, and you want to put your smallest residue at where the Berge-Dunitz angle approach of your nucleophile is going to be. In the case of the polar Felkin-Anh model, you want to put whatever polar group you have, a CO bond, a CN bond, halogens, etc. You want to put that group perpendicular to the carbonyl, and we talked about why that's the case, because you get the favorable overlap of your low-lying sigma star orbital with the pi star system of your carbonyl. You want to put that group, the polar group, perpendicular, and still have your smallest residue at the Berge-Dunitz angle for the approach of your nucleophile. And so yes, we've used that to predict the diastereoselectivity of several additions to chiral aldehydes and ketones. And this will be on our exam next Friday. Tomorrow in class, Kevin will be presenting, I guess, sort of the same material. He might talk about diastereoselectivity of certain additions to chair systems with heteroatoms in them. I'm going to talk to him about presenting that. He might do that, or he might just clear up any issues that you have with the Felkin-Anh and the polar Felkin-Anh model. Otherwise, I'll see you all at office hours in 20 minutes. I hope my phone didn't stop recording like 50 minutes ago. I'm sorry I went over time. Please, phone, record. Oh, it did. Good. 59 minutes, so not too bad. But yes, have a good fall break. Email me with any questions, and I'll see you on next Wednesday.